Thank you, Steve. All right. Hi, everyone. Today's talk, I need to learn how to use this. Where I'm here. So, a couple years ago, I started learning a new programming language. That was Go. I didn't know what to do, and I went and I downloaded some PDF from online and started reading it, and realized that a lot of people use Go to code some interesting stuff. Back then, I was using AWS, and I came about to know containers, Docker. Docker was my first container runtime. And through my exploration, I figured out that most of the code is written in Go, so I need to understand it really well. So I read it, didn't understand it. Read it twice, read it 3 times, 4 times. By the time I read it many times, I was able to put something together, and then I finally started to write code. And today's talk is about container networking. Docker being one of container runtimes, but there are other runtimes. For example, LXC. That's the container that runs the guest shell within, let's say, Cisco and XOS. There are other container runtimes, and for that, so each runtime has to plug in to a networking stack, and I will put, and what we'll do today, we'll brainstorm about those different concepts of container networking, and specifically Linux. Because container, Docker, all of those things are associated with specific technology, which is Linux. Linux is cool. It has some new features that were added, not so new, but newly added features that are called namespaces. And there are 7 or 6 namespaces, and one of them is a namespace called networking namespace. So if you think about it, each application is a process. A process has a reference in something called proc file system on the operating systems. When you create a container, you create a process, and that process, by virtue of namespaces, will get its own process ID that uniquely identify it. And when you're inside a container, you will be able to see your process as being number 1, although operating systems runs the process ID number 1. So how's it happening? It's happening by a mechanism or inside the kernel that when you create a new process, it basically allocates those namespaces. And one of those namespaces is called network namespace, NS. So what is driver? In theory, a driver is something that's defined in this Wikipedia article, but as it's applicable to container networking and Docker, a driver is something that enables you to interact with a virtual device. Because if a runtime is a process and you want to interact with other processes on the system, you have to have some kind of a device that helps you do that. So for example, one process streams packets to another process. How do they do that? Well, a very basic way to do that is to create a pipe, and pipe usually has 2 ends, so one process will stream into the pipe and another process will capture or receive packets on the other end of the pipe. So Docker has pretty cool implementation, a mechanism to make processes to interact on the network layer. So what we'll speak about is something called CNM and CNI. So container networking model and container networking interface. In container networking in general, there are 2 models. Those are the names of the models: container networking model, container networking interface. So how's it happening? Because Docker was first, so they picked up container networking model. But the reality is there are 2 models. One that's spearheaded by something called Cloud Native Compute Foundation, and another one is spearheaded by Docker themselves. So they have this repository on GitHub. It's a LibNetwork. So LibNetwork is the driver. And what you see there, those are directories for each individual drivers within this LibNetwork ecosystem. One of the drivers that's mostly important to this audience is the one called remote. Because remote allows you to extend the functionality of Docker and allows you to configure, to extend Docker's LibNetwork functionality to other things that may not be in Docker ecosystem. A simple example would be Open vSwitch. Open vSwitch is a virtual switch that runs on systems and allows you to communicate to upstream controller over OpenFlow. So remote driver allows you to, allows Docker rather, to call an external API, and if that API understands a protocol, a model of interaction, it would be able to configure that Open vSwitch with VXLAN ID, the previous talks, right? VXLAN ID. It would be able to configure routes, perhaps. It may, like MAC address, something, update MAC address table, those kind of things. So that's really extends the functionality. So remember, driver and plugin are synonymous if you read about container networking. So plugins are the ways to extend things. So once again, LibNetwork is a driver. It has built-in drivers. One of them is remote. And then that remote driver has an interface to call external system. In CNI, in container networking interface, a different model. They have a different interface. It's actually a different implementation. What they do there is that they decided that they would do it different than Docker. And they came up with concept of binaries. So every time you interact, you want to create something on the network, you would run it through a binary call. So you will basically run an executable, and it will do the work for you. On the Docker side, it works a little bit different because on the Docker side, it will actually be running all the time. While in CNI, it runs only when you invoke it. And I will explain later the differences. So if you think about it, container networking CNI, that's a main repository that explains the specifications of container networking interface. Within that, there is a directory called libcni, which really provides you the driver, one of the implementations of how to implement libcni, but that's not the only implementation that exists on the market. For example, Mesosphere has something called forgot the name, some kind of a different method of utilizing that model. So different other orchestration platforms like Kubernetes, they may create their own. So then you have a different repository on the GitHub that would be container networking plugins. And you have two kind of plugins, network plugins and IPAM plugins. On the network side, you have the regular bridge plugin, IP VLAN, MAC VLAN, those things. And on IPAM, you have either host local or DHCP. Now, the important thing, when you will be building those binaries, those executables, you will likely to download both of those repositories from GitHub. And when you will be compiling them, you will basically, for each of those drivers, you will have a single executable. All right. So at the moment, when I first looked at it and I tried to understand what's the difference between CNM and CNI, I really thought it's some kind of like a war between two cultures of some sorts. But there is a story behind it. And the story, in my interpretation, is that container networking model would be used by companies that really run strictly Docker. They're not interested to run any other runtime. If you think about enterprise computing, if you want to support, let's say, 5 different types of switches, it's very hard in a data center. So you usually stick with a couple of vendors, right? Same idea here. You stick with with Docker as being your container runtime, so you inherit that model with you. And likely you will not use container network interface. Container network interface is used by someone who is running an environment where they have to manage different runtimes for different people. So imagine that you're a big service provider, I don't know, any kind of, and you need to support Windows and Linux. And you need to support different runtimes, a Windows runtime and then Linux runtime. So for that, you would go with something like Kubernetes, Mesosphere, those are what I call orchestrators. And what orchestrators do, they run agents on every system that they want to run Docker, and when they run that agent, they pass certain options in their command line. So one of the options could be use CNI or use CNM. And that's really the difference. So someone thought that it's easier for the industry of container service providers to use CNI. They also avoid vendor lock-in the sense that if you only use LibNetwork, you might be at risk that Docker would set the rules for you. So CNI is a specification. So in material terms, you have a file. It's a JSON file, and it has to be in a certain structure. What it does, you provide to it the network definition. That's all it carries, a network definition. And it has references to the drivers that network definition would use. So whenever you deploy, orchestrate your networking with container network interface, what you will do is on each host, you will put an orchestration agent. So there will be like some kind of master-slave topology where you have a bunch of slaves. Now, those orchestration agents will talk to orchestrator, which is Kubernetes, maybe Mesos server. There is a new thing in town, Nomad. And when they talk, they basically can call the master, or other master would call to the slave and say, run this command for me, and I want you to use the bridge driver, and here's a network definition that I want you to use. The drawback to that is that you have to populate network definition on every host that you deploy that thing. So each agent has to carry that pair of network definitions. So when master says deploy a container with IP 10.10.10 on my network, what it has to do, it has to say Docker run and set the networking to none. So what will happen is that Docker, LibNetwork, one of the drivers, would create network namespace specifically for that process, but will not configure it with anything. There will be literally a loopback there. That's all. But then orchestrator, knowing the idea of that container, of a newly created container, would execute follow-up commands. Now, how does Docker know about that network? Once again, it's a definition that has to sit on the host. How does it know about the subnet mask, et cetera, et cetera? It's also, all of those definitions have to be populated on the host. So when you run your container and you specified, I don't want to use Docker networking, what the orchestration agent would get is a sandbox key. Sandbox key would be the path to where that namespace, network namespace, located in the file system. It's actually a set of file descriptors. The last command there on the screen, it's basically, this is how you invoke a CNI plugin. In this case, files are located at etc in the etc CNI.d. And the reason I didn't post that file is because you can find it on GitHub. You can go on GitHub, and that's basically would be the file on the first landing page. What you have to say to it, to that binary, is that when you call a binary, you can pass environment variables into your executable. And here we pass 5 environment variables: CNI command, CNI container ID, CNI namespace, and the interface that you want to use for the container, as well as the path for other binaries. Although in this case, we only call bridge driver. Why do we need that? It was kind of tricky for me to understand, but the idea is if your network definition says, I want to use bridge driver, but I also want to use for IPAM some, let's say, DHCP, somehow this binary has to find where that another binary located. So that's a bit clumsy for my taste, but at the same time, this works. So what will happen is that that executable will connect container ID and container path to container's network namespace, and we'll configure it. And then you would get, your plumbing for the container. So when you enter the container, it will be configured with an IP address, and it will configure IP tables masquerading, right? And you will have connectivity out of the container and to the container. So remember, once again, that orchestrator is in charge. This is very important because in this case, although you're running Docker, and Docker engine is in itself a process that's basically an agent, you now have to run a separate process that would be part of like a slave process on each host that would be taking commands from orchestrator. Sometimes it's great, sometimes it's not. It's all the trade-offs that someone has to make when they design a network, a service provider network for container networking. CNM, that's my favorite, so I'm a little bit biased. So in CNM, it works with a very important caveat. With orchestrator knows the entire topology of where the containers are, what kind of IP addresses they use, what's configured on them, et cetera, et cetera. In container networking model, Docker acts as an agent. And there is a mode that they recently called it swarm mode that allows you to achieve the distributed networking with CNM. So imagine that you're running Open vSwitch. That Open vSwitch connects to a controller somewhere on your network and communicates OpenFlow. You have to be able to configure. The first thing you want to configure is that you need to know, in order to communicate between two endpoints, you have to know VXLAN ID. That's basics, right? And then, so you would be able to encapsulate, and VTAP IP address. So this way, you would be able to send the traffic to VTAP IP address with the proper VXLAN ID. So a packet could be decapsulated and brought into a specific container if necessary. So in container networking model, Docker decided to use something called key value store. Key value store allows you to store network information, both for networks and for containers. Now, imagine that you have a definition for a network, and you want that definition to be consistent across multiple hosts. What you would need to do is you need to ensure that that definition is copied to every single device on that network, and also you have to watch for overlaps, because if I want to provide an IP address of 10.1.1.1, I need to make sure that no one else has taken that IP address. So key value store has the information, number one, about the containers on the network. Number two, it has information about the networks. So if at any point of time you sit on a Docker node that's part of that cluster that communicates to key value store, when you do Docker network inspect, it will show you all the definitions, network definitions that are in a key value store, whether it's etcd, whether it's console or Zookeeper. At the same time, when you do Docker network inspect, when you inspect network from a host in a cluster, What the other benefit you get is you see all the containers, you know, all the IP addresses that were assigned to all the hosts that are connected to that key value store. That key value store is very important because imagine that you run not one, but 100 different clusters. And in each cluster, you use same exact network. So when you store that network in key value store, you have to make sure that the network somehow is somehow uniquely identified. So you would add some kind of salt that would say to you that it would be an IP address plus some other string that would uniquely identify that network within the key value store. And now when network definitions are put into the key value store, all of them are stored, the keys themselves are encoded with base 64. So when you yourself look into the key value store, sometimes you would look for networks, but what you would see is a long strings. So the reason you see that is because it's base 64 encoded, so you have to decode it. What's a disadvantage of that model? So once your connectivity to key value store is broken, you are basically in a split brain scenario. So you have to watch out, and your design has to preclude you from being in that position. So you have to do everything in order for you to keep your hosts in sync without split brain. So container networking model, the Docker runtime. So when you actually type commands in Docker, let's say you type Docker run, what will happen is that this is a CLI, and your command goes to something called Docker proxy. Through the process, it ends up in a library called LibNetwork. Within LibNetwork, there's a driver called remote. And that remote driver has an ability to add remote plugins. And there are two types of plugins that are applicable to our community, which is network driver and IPAM driver. Now, IPAM driver is nowhere in documentation. So one of the things that it's really important for you to be connected to GitHub and sort of read information there, because that's your only source of documentation. There is no RFCs or things of that nature. It's basically what you read. Your ability to read code defines whether you will be knowledgeable about that thing or another. Unix domain sockets. At the very beginning of the Docker, the way you would interact with a host would be through a socket that was published on a specific port, and it was exposed to the networking stack. So in theory, you could have, from your machine, connected to Docker proxy process by utilizing the port that was exposed on a network stack. They changed a lot, Docker changed a lot, and in lieu of security risks, they no longer do that unless that's not the default. And what happens, the Docker socket, Docker interface itself is a Unix domain socket, sits on a local system, and someone from a remote system cannot get to it. So here are simple commands to curl commands to connect to a Docker socket and run commands. Oh. The previous slide was you would use curl if you have a recent version, and it's able to connect to a socket, and it's basically a web server. Docker proxy is a web server. Docker driver that uses CNM is actually a web server. So it's a web server that is served on a socket instead of a sort of IP address. Now, driver versus plugin. People get confused. They think it's two different things. It's actually all one. So driver, plugin are used interchangeably in the documentation. One of the things to understand is that Docker engine itself communicates to key value store. At the same time, it has to communicate to two plugins, the network driver plugin and IPAM plugin. And and each of those plugins can reside on the same socket or on two different sockets. There are advantages to that. The advantage of being on the same socket is you can control, so let's say you distribute an IP address, but then once you allocated an IP address within your processes, within your application, you basically can note what endpoint ID was assigned to a port. Or maybe you can get application level information, which is great, but at the same time, you create a monolithic driver that sort of combines the networking stack and IPAM stack. So for everyone, so it's better to split, in my opinion, but you see a lot of drivers there that are sort of like plugged in together. So the reason people do that is because you might need IPAM information to configure network port and vice versa. So for that reason, people combine. I advise against. So there is an important thing about network driver is a scope. So when you deal with Docker plugins, when you run Docker Network OS, you would notice that there is a scope thing, local and global. And I never understood it myself until actually I read the code and tried to figure out, like, why do we do that? So it's actually a VRF. So to connect the terms, it allows you to first to say whether if it's local, you are using local key value store, which is in Docker is BaltDB. And if it's global, you use global key value store. And remember that when you use global key value store, means you get network definitions for the entire network. That's how you synchronize. So if your network scope is local, you basically, like your network stack is entirely local. You don't share information. If you deal with BGP, VPN, OpenFlow, controllers, if those keywords pop up on your radar, likely the driver is global, meaning it will store data in a global key value store on the right there. Now, the libkv is not a key value store. libkv is a library that Docker developed to interact with key value store. So it's better to say that the value on the left is actually BaltDB, but libkv is the mechanism that allows for the Docker engine to interact with key value stores, whether local or remote. So when you try to create an overlay network, a network using overlay driver, and you are not connected, your Docker engine is not connected to distributed key value store, global, you will end up with this message. It means that the network definition is global, but you don't have definitions of that key value store for me, I will not be able to create that network from the get-go. So remote, one of the things that I wanted to emphasize during this session is I wanted to create a driver, an IPAM driver, and how did I do that? So one of the things that when you start coding driver, you have to run a web server, and you have to make sure it runs on a socket. So you basically create a socket and you bind that web server to that socket. By default, Docker looks on startup. When you start Docker, it looks into the directory run Docker plugins and tries to find .sock files. However, there are two other ways how Docker can find a socket. A second way, if you drop in that plugins directory a JSON file that provides a definition, like a description for your driver. I didn't see anyone using that, but that exists. And the third, the most coolest thing, is that you can create a definition for a driver that's remote. Like that's located totally on a different host. So you would end up with a single file, and there you would have the URL to a remote web server that would be able to serve those requests. Plugin type. So as I described before, there are two types of plugins, network driver and IPAM driver. So in this case, it's an IPAM driver. When you create a network, let's say I create a network that uses bridge, but I want to use IPAM, my own IPAM. Let's say I want to add static IPs for a specific workload, and I don't want to rely on the IPs that, that Docker gives me. So I coded a driver, and the first thing that you would see in a session when Docker starts up, it will look in the directory and it will make this call, plugin activate. The reason for that call is to notify the driver that Docker starts up. There is no need to respond to it, but now driver knows that, oops, my Docker just restarted. It could be used for things like rediscover ports, performing audits, things of that nature. Then there will be a call to get IPAM driver get capabilities. So that call instructs the plugin to provide two instructions to it. One is whether the plugin requires for the Docker to generate a MAC address for the container. Otherwise, what you want to do is, I don't want Docker to provide me a MAC address. I want to create my MAC address myself. Where that comes into play is that imagine that Docker generates MAC address itself, but then without realizing that somewhere else that MAC address is in use, you now have layer 2 conflict somewhere. So for the most part, I see that requires MAC address would be set to false, and requires request replay is a feature that if you set it to true, Docker on startup would request and release all the networks that it knows about. Now, get default address space. So imagine that you have, remember that slide where you had the networks has two scopes, local and global. However, they also have identifiers. So there is a thing called default address space. That's what I called VRF address space. So it would be something that a plugin can say, this identifies the global space of this instance of a plugin. An example would be, let's say you run two drivers, one from one vendor and another one provided by a different vendor. And both of them use global equal global. So now Docker would think about those two drivers as being the same. Why? Because the identifier, the global identifier, is the same. So if you will be running multiple plugins on the same box, make sure that the address spaces are different between each instance of a plugin. That also allows you to run code. Same plugin runs multiple replicas of that same plugin. Let's say you want to provide network segmentation and isolation. You would run a plugin for, let's say, red network, for the blue network, and for the green network. And when you do that, for each of them, you assign different global values, because those are the values that you can later on populate to the key value store, the global key value store that they all share. Here is how the network gets requested. So when you remember, we run that command, Docker create network. So first thing that happens on the actual physics of it is request pool. So here, the pool ID is 10.4, and there is a subtle thing there called options. So someone yesterday told me, reminded me about radius. So think about like key value pairs. So in the options, you can pass on key value pairs, and those key value pairs would end up being stored in key value store. Now imagine that you run BGP process, and you want to advertise your container IP addresses to the network. One way of doing that is to run an agent on each and every host. Like something like Go BGP, you would be able to establish a session and advertise the addresses. But another way to do that same thing is to monitor key value store for the changes and have maybe 1 or 2 sessions for the entire cluster, but achieving the same propagation with less sessions. Next thing that happens is the request address. When you request the address, so we are still in the network, but now there is this request address call. First, it threw me off when I saw that, but then I realized that actually for default gateway, Docker requests an IP address. So when you create network, you actually make 2 calls. One call to create the pool, to create the network. Another call is to allocate request address for the gateway. How do I know that? You see request address type, and then you have com Docker network gateway. That same mechanism is to use to, let's say, to pass information about a MAC address. Let's say I want my container to have a specific MAC address. It will be passed in through the options. Well, so next thing we do, we'll start our first container on that mynet, and we want to start it with specific IP. When I stop that container, so I started the container, but when I click stop, what will happen, Docker would release that IP. So important distinction, IPs are not released when you remove the container. IPs are released when you start the container. It means that in any kind of distributed work, when you stop a process and you reinitiate the process, unless you have sophisticated IPAM mechanisms, you might not get the same IP address, although at the start you got that. So that's the next, oops. When we remove our network, what happens there? We get, first thing, so remember, when we requested our network, we also requested the IP address for the gateway. So the first thing you do when you remove the network, you actually do the release of the default gateway. Why it's important? Because maybe that should be the trigger, let's say, for some other external mechanism to synchronize other network information. And after that, you have the release pool call, which is basically releases the network from the Docker instance, but also if you use a global scope for the created, it will also remove that from the key value store. Common issues with IPAM in both models, if there are static IP addressing is an issue, scaling. So imagine you're starting a container with a fixed IP address by passing --IP. When you want to scale that application, it will actually pass the same address. It will be the exactly same assembly that gets populated and gets run. So when that happens, chances are you would not be able to get that same IP because it was already taken by the initial instance of it. When you will try to do the traditional technique, which is basically MAC address, IP address mapping, it will also not work for you because your assembly will try to use the same MAC address, and Docker would fail to provide service because it will say to you, well, that MAC address is already taken. Lack of endpoints. So what you want to see is you want to be able to query for metrics, for versions. You want to be able to know the leases on the MAC address. The configuration, you want to be able to shut down the driver, and all of these things, those are common. How do you write? Here are the things that you need to worry about when you write a driver. So you need to worry about key value store, you need to worry about virtual switch, and you have to be able to synchronize that yellow layer. You have to be able to synchronize the information about network ports, because if someone removed the container, but that information did not propagate to the virtual switch, for example, then in case of Open vSwitch, you will still have that port as being alive. So most of you are senior people in the networking industry, and what we lack, from my perspective, is mentorship. So I want a mentor, and there are hundreds of other people that want mentors. So please participate on GitHub, on Slack, engage with younger people, and try to bring your values, the things that you collected over the years, to their table and share that with them. We have meetups in New York, so like we have NANOG today. In New York, we have NYNOG. And if you have any questions, ping me on GitHub. Thank you.